talking about locally potentially equivalent Galois.
Yeah, so, okay, it's on. So first of all, my thanks to the organizers. I think only Ashay is there. So thanks for the invitation to speak here and to participate in the workshop and conference. It has been a very nice time. And okay, so I'm planning to talk about some joint work with two people, different papers. With Plawam Das, he's there in the audience right now. And another one with Vijay Patanka. So the idea is to, with Plawam, it's so Plawam Das, it's a work generalizing, say a generalization of Faltings finiteness criteria. I'll come to it. Elliptic representations, and here with Vijay, it is this is some work on refinements of maybe let's say kind of multiplicity one, strong multiplicity one or something. I hope I'll have time to. This was done by me for the case for equivalent representations long back, 98. So we extended it to the case of potentially equivalent representations. So let's define. So what I want to say, so suppose you have gamma is a group, and you have two representations, say ρ1, ρ2, or two representations of gamma into some GLN of a field. If then you say that ρ1 and ρ2 are potentially equivalent. That is, let's say T. If there exists a subgroup gamma dash contains a gamma of finite index, such that ρ1 restricted to gamma dash is equivalent to ρ2 restricted to gamma dash. Okay, so that's a notion of potential equivalence. And now if you take K as a number field, and so say V is a V finite place, or any V place of K, so then you have so GK is the absolute Galois group of K. You fix a algebraic closure of K and work with that. And for every V, you can look at the conjugacy class of decomposition groups. So a decomposition group at V. And so suppose T is a set of places of K. So then you can say that, and you are given to say ρ1, ρ2 for the time being. Let me just make or two continuous semi-simple representations of GK, say into GLN of QL. Say continuous semi-simple. Say all my representations will be semi-simple because we'll try to derive the representation back from its character value. So then standard assumption is to take semi-simplicity assumption, and we'll say it's locally potentially equivalent at the places T if the ρ1 restricted to GKV, whatever it makes sense up to conjugacy, is isomorphic to ρ2 restricted to GKV. Right? So, okay, so just remark, if an addition, suppose if V is unramified for ρ1 and ρ2, and so I'll denote by ρ1 sigma V, say ρ2 sigma V of the Frobenius conjugacy classes. No, saying that ρ1, so ρ1 restricted to GKV is isomorphic to ρ2 restricted to GKV. In this case, it amounts to saying if and only the Frobenius conjugacy classes differ by roots of unity. The eigenvalues of the differ by roots of unity. Okay. So the kind of questions we want to look at is conditions on T to ensure where T is not necessarily the full set of spaces, but T is either a large set or a finite set, so that you can say that either some finiteness type of results on the set of representations which are locally potentially equivalent. When will they be globally potentially equivalent? Right? That's a kind of thing which you want to say, that if it is locally potentially equivalent at some set of places T, then can you say there are only finitely many? That is the kind of thing which Faltings will be talking about. Or whether you can say they are in fact globally potentially equivalent. So that's a kind of results we want to talk about. So let me first say some things about some kind of character theory or whatever it is. Or potential equivalence. So of course, two representations of a semi-simple representations of a group are equivalent, linear representation, if only if their characters are equal. So here we just want to extend it. It's not too difficult. So let's, I'll just recall this. So suppose M is a natural number. So we let the M power character or M trace character, M power character be the, and rho is a representation of this thing. So rho is a representation of gamma to some Jn of some field F. So F will always be of characteristic 0. Characteristic of 0, F is always 0. Right, so then the character is so chi m rho of G is just trace of G to the power n for G income. Okay, so then the first proposition is that so our representations are semi-simple. That is always the thing. So so ρ1 is potentially equivalent to ρ2 if and only if there exists some M such that chi ρ1 M equal to chi ρ2. Okay. So of course, this implies that is easy because it's a finite index. So some power M will work. So what you have to say is the opposite idea. And so this is standard. One way to get it done is to do the following. What you do is you look at the diagonal embedding, or rather the product embedding. So you have gamma going into GLN F cross GLN F. So this is rho 1 comma rho 2, rho 1 cross rho 2. And so, one notation given representation, I'll say that rho, I let G rho or whatever it is a Zariski closure inside GLN of the image of rho gamma. Okay, so the way to, so what we do is to change the problems to some problems in algebraic group theory. So what you do is you look at, so here you take rho equal to rho 1 cross rho 2. Of course, GLN cross GLN, so I can take the Zariski closure inside GLN cross GLN also. So I'll just continue to denote it by G rho. So what you have is that you have a representation of gamma to G rho of F, and then you have two representations. So from G rho, there is a map, first projection to GLN, and then the second projection to GLN. And so when you compose, so this embedding, this will give you, this is rho 1, this gives me rho 2. Okay, so the fact that our representations are semi-simple and whatever it is, so G rho naught is the connected component of G rho. And is a finite index. Right? So now these are basically algebraic functions, linear functions, some kind of algebraic functions, polynomial functions on this space. So chi rho 1 of M equal to chi rho 2 of M on gamma. Okay, so what happens is I can look at so gamma intersection G rho naught. So that's going to be of finite index. In gamma. Or rather, so this is going to be this is Zariski dense in G rho naught. And this being algebraic functions, so this implies that chi rho 1 M equal to chi rho 2 M on entire G rho naught. Because they are Zariski dense. And this implies that rho 1 is potentially equivalent to rho 2. So it's a fairly easy thing by using the basic theory of algebraic groups. That, of course, to say the characters are equal, so this implies that rho 1 restricted to basically the inverse image of, you have to, whatever it means correctly, gamma intersection G rho naught is isomorphic to rho 2 intersection. So this notation is not correct. You have to take the image, pull it, intersect it, rho gamma with G rho naught, and then pull it back. Okay, that's basically. But whatever I mean is whatever are the elements of gamma which maps into G rho naught by this. Yeah, so that's of course we are assuming always the representations are semi-simple. So this implies that rho 1 and rho 2 are potentially equivalent. The second reduction we get. Second reduction is we can talk about, see, when I'm looking at this Frobenius conjugacy classes, I said that, so what we are getting is, say, V unramified. We know that rho 1 saying potentially equivalent is equal to rho 2 is conjugate to rho 2 sigma v to the power nv. Right? So this nv can vary. Nv can vary with v. Okay, so it's a consequence of the fact that so the fact is there are only finitely many roots of finity in any local field. Local field and also only finitely many extensions of any degree. Non-Archimedean local field. Okay, yeah, finitely many extensions of given degree of a given degree. So if you use this two conditions, so you get the following consequence, corollary. Corollary means consequence. So let's call this. So let me say one more definition. So I'll say that definition if you want. Suppose rho 1 and rho 2 are element-wise potentially equivalent. If for any G in G, there exists some natural number Ng belonging to, so that rho 1 to the power G to the power Ng is conjugate to rho 2 G to the power Ng. Or you can ask for traces. So there is a, okay. And so let me say that I'll just state this. So the corollary of this fact is that suppose rho 1 and rho 2 are representations of gamma to GL and F a non-Archimedean local field. Of characteristic 0, then and they are element-wise potentially equivalent, implies there exists some M which is independent of the thing, such that so that such that the characters are equal. So if you want chi-rho 1, M is equal to. So no, I will just say that there exists an M so that rho 1 of G to the power M is conjugate to rho 2 of G to the power M, right? Which implies the characters are equal. Chi-rho 1 M of G equal to chi-rho 2 M of G, which implies rho 1 is potentially equal. Okay, so if you are working with representations which are valued in non-Archimedean local field, then you can, so element-wise potential equivalence will imply potential equivalence. Okay, so that's yeah. So I just wanted to say some few things about. There's one more fact I wanted to say. I'm suddenly forgetting what is. Okay, so anyway, let me come, forget that, let me come to this. So now I try to come to work done with Plawam on Plawam Das. So what Faltings, see for instance, so on the way to Faltings showed that suppose you have given a K is a number field, S is a finite set of places. Say S contains S infinity, of course. And if you are looking at representations, so let me say what is so V does not belong to S, and we are considering a representation rho of the absolute Galois group, say to GL and QL. So we say it's pure of weight, say W, and degree bounded by D. If the eigenvalues of rho sigma V or algebraic integers of degree at most D, say eigenvalues, say alpha, or algebraic integers of degree at most D, and for any embedding of Q bar into C, mod of alpha with respect to this embedding, say tau alpha is equal to so the residue, so I should say, so V has some, so it's the residue degree QV to the power W by 2, where QV is equal to the residue degree. Okay, so then what the Faltings finiteness theorem, Faltings finiteness theorem is to say the following, that there exists only finitely many, there are only finitely many see continuous and simple representation, many rows. So here I'm fixing QL. L is fixed, that is the which are unramified outside S. And pure of weight W degree at most degree. Okay, it's a kind of very nice application of maybe Nake Aslama and Chebolzuer of the Hermite-Minkowski theorem. So I'll come to that proof a bit now. So what our motivation was the following, is to what we are interested in is improving the following. So we extend this theorem. So the theorem we would like to show is, so we have fixed S. So what the theorem, so let's say the theorem. Let me write it here. So, the kind of mild generalization of this. So we want to say there are only finitely many rho up to potential equivalence, which are of course, so here we are not going to say where the inertia outside is. X by scalars. And of course, I'm pure of weight W and degree T. Okay, so this is the theorem we prove. So consequence of the thing. And the reason, one of the reasons for looking at this theorem was what had happened was there is a result of Baaziz and Boxall. So what they were considering is, you want to produce curves of higher genus, which are, or number fields, which are everywhere unramified. Okay, so that's what they were trying to do. Of course, you can't go to the Jacobian and do it. It's a more finer criteria, but let's not get into that. But in the process, what they said is, okay, that is difficult, but let's try to modify the question. And so they're asking is, suppose you have two curves, a curve X or a variety X defined over a number field. Okay. So then you instead of saying whether X or KV is unramified, what they are looking at is, what they said is twist unramified. If there exists a form X dash, which is also defined over KV. So form X dash meaning this, that means X dash or KV bar or KV is isomorphic to X or KV bar over KV, and X dash is unramified. And so then they use this to give examples of curves of maybe higher genus 2 or 3 or whatever, which are twist unramified, but or very small degree extensions of Q, like quadratic, I don't know. That's a kind of thing they were trying.
Do you allow ramification at infinitely many places for rho in your? Yeah,
here you can, oh yeah, there I can allow, but there's a old result of Shekhar and myself where we say that the set of such places is of density 0. So that doesn't really come into the place. If you are assuming semi-simple Galois representations, right, into JLN F, then the set of ramified places is always of density 0.
But it can be infinite.
It can be infinite. That is the Ravi Ramakrishna's examples. Yeah. Yeah, right. Yeah, I should have, yeah, S can be, yeah, right. But that doesn't play much of a role because it's density 0, one can always keep throwing it out if you want to. In some. But here it's a different. Okay, so what's happening is that so we can ask similarly, instead of looking at the variety, you can look at the representation rho, and you can say that saying that two representations are isomorphic, or if I look at it from the point of view of Galois representations acting on the cohomology, this amounts to essentially saying potential equivalence. But what we are going to look for is some kind of, instead of potential, we are just saying that the inertia is acting by a scalar. So we are saying a slightly more restrictive condition, saying that there is up to potential equivalence, the representation becomes unramified, but by a finite order inertial scalar. So that was one of the kind of motivations for us to look at this kind of results. Okay, so let me give an idea of, sorry. Yeah.
If you put a bound on the degree of extension over which it becomes equivalent, then you still have finitely many, or?
Yeah, no, see, that degree is bounded because we are working over representations of characteristic, in non-Archimedean local field. So basically, there is a uniform M which will say that things will work out, because there are only finitely many roots of unity and finitely many extensions of a given degree. So it's a very simple argument.
Okay.
I'm not, once you know these facts, it's easy to see why it should be true. So the degree becomes kind of uniform. Yeah, so that's what helps in the setting, right? Yeah. Because we are working with representation in non-Archimedean valued fields. Okay, so let me give an idea of the proof. First, Faltings proof is, it's very clever. It's a very delicate argument. Yeah. Oh, many times I look at it, I still can't quite get it. How it's, quite get it. I mean, it's a very nice. So what Faltings? So let's just look at what is Faltings proof. Okay, so the Faltings proof is Faltings proves the following theorem, Faltings theorem. Okay. So I'm fixed. You fix your number field K, S, M, and say you're fixing QL. Okay. So then there exists a finite set of places T of K. Say disjoint from S. So let me say always finite places. Such that the character values at the finite set of places determines rho. Okay. So rho is of course semi-simple representations. All our representations are always semi-simple, such that given rho1, rho2 from GK to say GL and QL with character chi rho1 of sigma v equal to chi rho2 sigma v for v in T, then this implies rho1 is equal to rho2. Okay, what Faltings is saying is that given your number field, your finite set of places in natural number n, and you fix a, basically here you need a non-Archimedean local field so the residue degree is bounded. Okay, that's all. So then there exists a finite set of places T of K. Okay. So that is fixed once and for all, once you are given this data. Fixed meaning you can choose a finite set of places. Disjoint from S such that given rho1 and rho2 from GK to GL, with whose character values agree at sigma v at the places at in T, then the representations are isomorphic. So once on top of it, if you are also given purity, say if you are working with bounded degree, suppose you know that the Frobenius eigenvalues are of, suppose the characteristic polynomials are integral of bounded degree. So you know that then the coefficients of the characteristic polynomial, suppose if they're integral, and if the weights are bounded, they will all be bounded. So then there are only finitely many choices for the characteristic polynomial at any place. So then there are only finitely many choices for the abelian variety, or any variety which is pure of this. So from this theorem, the other theorem follows from basically that there are only finitely many algebraic integers of some bounded degree and bounded, or not finitely many algebraic integers, finitely many, anyway, characteristic polynomials which are there. Okay, so that is theorem of Faltings. So let's see what is the proof of this theorem. So this is the proof of this theorem. So what you look at is consider the image this inside say ZL of ρ1 cross ρ2. So I should say contained inside GL and QL cross, or not GL and QL. I look at the consider the ZL module. Generated by ρ1 cross ρ2 of the Galois group of K contained, right? So that is contained inside GL and QL cross GL and QL. But ZL module generated inside MN QL cross MN QL. Okay, so it's a free module of rank. So let me call that module M. So it's a free module of rank at most less or equal to. This is n squared, so it's 2n squared. Okay. Okay, so then, so what you're looking at is you consider the n is a submodule of M on which the two traces agree. So our aim is to say that n equal to M. So you want to know whether n is equal to M, and aim to say n equal to M. And so by Nakayama, suffice to say that n bar equal to M bar. That is the image of n in M mod MM is equal to so this is a local module, so I should say M mod MM equal to M mod MM. Okay, the image of n is equal to the whole module, right? So now what? So this, so the image. Okay, so now so let me say, let T be the, so now let me say, consider the collection. So let L over K be a field unramified outside S and of degree at most L to the power 2m square. Okay. Now Hermite-Minkowski says there are only finitely many such fields. There are only finitely many. Okay. So now right? So what you do is, so let T be a set of places, finite set of places. So I can set that the conjugacy classes in T, the conjugacy, the Artin elements in T, Artin classes in T cover each of these Galois groups. Galois group of L over K. Right? There are only finitely many, so you can choose a finite set so that you can take the compositum of all these fields and you can have a finite set T so that its image will be surjective onto the Galois group. That is, it will pick out each and every conjugacy classes. Right? Now, if I look at the image of rho L, this row of GK inside M mod MM, of course, this is a group, so it will go in invertible. And this is going to give you an extension which is unramified outside S and of degree bounded by at most L to the power 2n square. So at those set, by assumption, you're assuming the character values agree. So then the character value will, so that means that set is going to span the entire M mod MM. And so it will be trivial. So that is essentially Faltings proof, which is there. Okay. So now what you want to do is to modify this for the, when the inertia acts by a scalar outside. So the observation is that, what is the main observation is that Newton identities so express the M power character. The M power character is not really a linear character. As an integral combination, integral linear combination of characters of the form that is basically you're saying that you can write it in terms of elementary symmetric function. Any symmetric function can be written in terms of elementary symmetric function in particular, but the point is that it's integral of the form. So you look at, suppose if I'm working with the vector space V, so it's better to say it. So I look at X sphere R1. V tensor X sphere R2, V tensor so on. X sphere RKV, where R1 plus R2 plus RK equal to M. Okay, so you range over all R1 plus R2 plus RK equal to M, take some standard V tensor exterior square, some number of copies, and say that these aspects are all equal to M. Okay, so then basically what you do is we do the Faltings theorem for every such representation. Okay, and then when you sum it up, you'll get that. So, okay, so here what happens is, notice on this, I should say that this is very important. On this representation, because the scalars are of order, I hope I've said my theorem correctly. Yeah, okay. So I have to choose an M. So the M is, so the M is chosen because of the finiteness of local fields. M is chosen from the proportion given above. Okay. So once you choose an M, because I know that the M, if it is locally potentially equivalent, then the M, there is a fixed M for which the conjugacy classes will differ by the roots of unity. So, so here I'm assuming that the inertia is, so I should have said maybe the inertia is acting by. Yeah, I don't know whether I've stated my theorem correctly. So I'm saying inertia outside S acts by. Yeah, sorry, I should be very, very careful. I think I've been completely wrong. Yeah, it acts by scalars. Yeah, so the scalars of bounded order, yeah, I've said that. Okay, scalars are of bounded order. Yeah. That's not, that is too, that's easy to, it's just, M is bounded by the number of roots of unity. So then on this representation, the ρs will be unramified outside S. ρs are unramified outside S. Okay, so you can apply Faltings to each of these representations. Then apply Faltings. Faltings method. To each of these. Okay, so that's what gives you this finiteness, which is there. Yeah, anyway, so this is, let me see. Okay, I don't know, I have some 5 minutes left, or I want to say something about the work with Vijay, but that's in a kind of different direction. Okay, are there any questions or doubts on this? Yeah. No, I don't know. See, what kind of some questions which bothered us are things like there's this conjecture of Maser, where if you know one model representation is suppose sufficiently large, model representations are isomorphic, then the abelian varieties or elliptic curves have to be this isogenous. So that is one which is there. The other problem which bothered us, which is of course false, is that various things about potential equivalence, how much finiteness you can say. Right? So it is not true that if you fix a set of places S and you look at, say, elliptic curves or Q, which become potentially unramified outside the places above S, then they are finitely many. That is not true. Okay. Because the J invariant, if you see the saying, the J invariant can be pretty infinitely large. So that is not true. So then, yeah, so it is not clear what exactly one can, how much one can get by looking at potential equivalence. But then there are questions which arise naturally when you, where the Frobenius eigenvalues differ only by roots of unity and whether you can say anything. Yeah, so let me say the point is, for instance, Vijay. So let me just give a consequence, a theorem which consequence of what we had proved is that suppose you have suppose AB or abelian varieties. I am fixing a dimension defined over say K, and so T is a set of places of K of positive upper density. Let's say positive density. You assume, for instance, that AV is potentially isomorphic to VV at the places V and P. So that is over the finite field, KV bar. That means over KV bar, they become isomorphic. So this is just a question of the V. I can assume this to be T is unramified. Right? So potentially the Frobenius, that means the Frobenius conjugacy classes differ by roots of unity at a set of places of positive density. And then I'm also going to assume that rho A, the representation of the Galois group on the Tate module, VLA, say, suppose the image is connected. Image is connected. I suppose I hope this is correct. Yeah, the Zariski closure and the endomorphisms of B or K is equal to endomorphisms of B or K bar. So then this implies A is potentially equivalent to B. That is potentially isogenous. Potentially isogenous. The Galois representations. So this is a kind of thing which we wanted to do it without potential equivalence. I had done it long back with the abelian varieties with more general for Galois representations. The problem is that the theorem is not true without assuming this kind of assumption. So for instance, we can look at CM elliptic curves, then say by Qi, Zi or whatever it is, and then it will be some fourth power. One can show, because it's just a positive density of places, a set of places of density half when it's landing inside the non-connected component of identity, its fourth power will be basically a scalar matrix. Okay, and that see basically if I'm looking at suppose 0, 0, A inverse, whatever minus A inverse or determinant plus minus A inverse, so then the fourth power is basically identity in SL2. So this kind of examples kind of one can generalize. And so how much time I have? 4 minutes, is it? Okay. Yeah, sorry, I thought I had only 2 minutes, so I was just okay. Anyway, so so this example, so you have examples of CM elliptic curves. Which gives you counter examples. And so this was, and this example was, of course, in a sense, was indicated to us by Serre that we had earlier brashly said that things are okay, but it is not. So then these spaces are isogenous. So let me say what is how does one prove this theorem? So as I said, there are counter examples, but let me start by example. So what we do, So there's a result, basically following set. Again, this is my paper, the MRN paper of 98. So we have a kind of what may be called an algebraic Chebolzuer. So that might be of interest in general. Theorem. So I have rho is so G rho is my Zariski closure. So I have a representation, say rho from GK to GLN, sum of a local field, say QL. G rho is the Zariski closure of the image. And S is some set of places, whatever, ramified places and so. So now X is a conjugacy condition. It's contained, if you want, inside 0 or whatever it is. It's a conjugacy invariant, algebraically closed subset. Algebraically closed subset. For Chebolzuer, you need this some kind of algebraically closed subset. For instance, suppose if I take 0 is GLN, suppose G is GLN cross GLN, then look at trace equal to trace. Or even in GLN, you can look at trace equal to 0, that kind of condition. These are conjugacy invariant algebraically closed subsets. And then, so you want to look at the cardinality of the number of places, so the norm V is less than or equal to X, so that rho sigma V lands inside, say, XF or whatever it is, XQL, inside this, divided by X, the number of places. This probability you want to say. So the limit as X goes to infinity, that is a counting measure. So this is going to be, usual Chebolzuer is when you're looking at image is finite. Then you say it's the number of conjugacy classes which land inside X divided by the total number. So it is cardinality of the number of connected components G phi, which is contained of G, which is contained inside X, by total number of connected components, by cardinality of G mod G naught. This is 0, 5. Okay, so basically you have an infinite representation. If it is a finite representation, this is the usual Chebolzuer. But if you have an infinite representation, you replace it by the Zariski closure, and then you count. And as long as the condition which is you want the conjugacy class to land in is algebraic, closed, and it's of course invariant. It's a conjugacy class. So then you just count the number of connected components which lands inside upon this. Okay, so once you do this, so now the trick is, now what you have to do is what's called a unitary trick. Suppose I want to say equivalence only with m equal to 1, say m equal to 1. This is the old paper. What you need to show is that, so you know that suppose positive density implies there is a connected component G phi which is contained inside, for instance, trace equal to trace. Okay, but I am assuming also that the first rho 1, the G rho 1 is connected. G rho 1 is connected. Assumption. So you have a connected component G phi, G rho phi, which is contained inside GLN cross GLN. G rho phi, what are G? This contains a 0, which is contained inside this. And this has maps to G rho 1. This maps to G rho 2. Right? G rho 1 is connected, G rho 1 not. And this is a connected component maps, so it maps onto the connected component. So what this implies is there exists an element of the form 1, x which is in G phi. Okay. But now you go all the way to complex numbers and work with unitary groups and count the trace. So trace of 1 is n, and the only unitary matrix with trace n is X has to be identity. So this implies that the connected component of identity itself should be contained inside trace equal to trace, and which means the representatives are isomorphic, restrict to G0. But here what happens is we can't get 1, so you won't get 1, 1. What you'll get is the unitary trick will imply that it exists an element 1, j to the power m equal to 1. And so just one moment, I'll just say what the main trick is. Yeah, it took us a long time, 5-6 years after. So what this implies is that you have trace of rho 1 g to the power m or whatever it is equal to trace of j times rho 2 g to the power m. Let's say if you want g is in the connected component of it. Right? So let me put j out here. So what's, I don't know, I should say trace of rho to g to the power. So basically it's a condition that trace of x power m, so x power m is equal to trace of xj power m. And we need to figure this out. So the main thing is the following identity. So suppose if I look at xj square, that is equal to xj times xj. So which is xj times jx, you put j inverse times j square. Say m equal to 2, j squared is identity. So this implies that this is equal to x times jxj inverse. So this is equal to x times theta x. And theta is this automorphism defined by conjugating by j. So you can do it for any m. So what you get is if j power m equal to 1, then xj power m is x times conjugation by theta j of x times theta j to the power n minus 1 times x. So you get an automorphism of the group, and then you use a theorem on connected reductive groups that if you have a semi-simple group, if you have an automorphism, then the fixed points is always non-trivial. So that is a non-trivial reductive group of some dimension greater than 1. And then you can see that whatever you get, or the standard counter examples one can, which generalize the CM case, tensored with the representation. So you get, so it's not equivalent on the nose. There are counter examples, but the counter examples can be controlled. And so if you understand something more on various conditions, you can assume you can get potential equivalence, but I don't have time to get to that thing. There are various other conditions where you can conclude potential equivalence from locally potential equivalence at a positive set of places. Okay, I'll stop here. Sorry, I could not get to that.
Questions for Rajan? Can I ask a group, maybe just a group theoretic question, not a number theoretic question, but is it possible for two global continuous Galois representations to be potentially equivalent by some non-closed finite index subgroup, but not a closed finite index subgroup?
No, see, the point is one of these things about this kind of theorem will tell you that, the set of places where the traces coincide or whatever is actually a very good algebraic subset. So in particular, you might assume only a positive upper density or whatever, but it also says in particular the set of places where it coincides is the density in the usual sense. So it includes a lot of regularity that way. Once you say positive density, then the algebraic Chebolzuer kind of kicks in to say that, you will at least have a connected component which is algebraic, which is sitting inside. And that gives you a tremendous algebraic handle on that. Right? That's the thing. It is an application of the Chebolzuer. So basically there in Say's paper, but he didn't state it in this generality, but he, of course, it's there in once you see it, it's not. But this seems like a very useful theorem to know. It's a generalization of the usual Chebolzuer, but for as long as you put a conjugacy in an algebraically closed subset, then it's fine.